Hello and welcome to the particle model of matter GCSE exam questions. Okay, so these questions are taken from real exams and so we'll get started. Figure 3 shows a diver swimming in a lake. So we've got surface of lake, air above, water, 20 metres, diver. The pressure on the diver is due to both the water above him and the Earth's atmosphere. Well, that was a question on another paper, a similar one as well. The pressure of air on the surface of the water is 1 atmosphere. How many atmospheres of pressure will be on the diver at a depth of 20 metres? Okay, so let's have a look. Let's read that question again, because yeah, that's actually quite a long piece of text, really. So let's just get my pen here. Right, water above and the Earth's atmosphere. Because we've got atmosphere. Let's write this down, because yeah, this is a common question actually, because people forget about the atmosphere. Atmosphere plus water, okay? Pressure, of course. Right, so we've got 20 metres. It says 10 metres of water is equivalent to 1 atmosphere. Okay, so 20 metres, so we've got the atmosphere as 1 plus water. So 20 metres of water is 2 atmospheres. So it's actually 3. A lot of people would not get that correct because, yeah, because it does seem too tricky, doesn't it? You think, it seems easy, but it's kind of not, is it? A balloon is filled with helium when it is on the ground. The balloon is released and it rises through the atmosphere. Explain what happens to the size of the balloon as it rises through the atmosphere. Okay, so let's have a think about this. Let's draw it. It's a balloon. So as you actually increase in altitude, okay, that's the atmosphere. So this actually, the pressure gets lower. Okay, because there's less atmosphere above you. And also the temperature decreases. Okay, so as the balloon rises through the atmosphere, the outside pressure, right here as well, outside pressure decreases, causing the balloon to expand. But the temperature also drops with increasing altitude. So the energy of the particles decreases. So the balloon would shrink. So, and it'll be the net effect of these two. So the nets, the overall effects. Okay, so particle model matter is all about temperature, all about pressure like this. So figure 4 shows a container of length 6 metres, width 2 metres, resting on the floor. The weight of the container is 15,000 newtons. Calculate the pressure that the container exerts on the floor. So, okay, we've just got to substitute some numbers into an equation here. So pressure, yeah, it's force divided by area. So force, 15,000 newtons. The only thing we've got to do, it's 3 marks there too, is got to work out the area. So the area is just a rectangle, so it's just 2 meters by 6 meters. I'll put that in a bracket. So all we need to do is work this out. So 15,000. Okay, divided by 2, we know it's 12, don't we? So 1250 pascals. We told the unit there. Okay, so we just got to work out the area. Yeah, make sure we do that. Okay. The particles of a gas exert a pressure on the walls of a container. Which row of the table is correct when the pressure of the gas changes? So just talking about pressure at the moment, one thing at a time. So it says pressure of gas increases, number of particles colliding with the walls of the container each second stays the same. That's it. So which row? So pressure. Not seeing quite right, does it? So increases, also increases. Okay, that seems the right one. Okay, something like that. So pressure of gas decreases, stays the same. So pressure of gas decreases, and that increases. So talk about a balloon, didn't we? Okay, going through the atmosphere. So let's think about balloons on Earth for a minute. The pressure in here increased. There'll be more particles hitting the wall. So it's this one B. Yeah, it's one to sort of think about a little bit, that one. A digital thermometer gives a temperature reading of 23 degrees Celsius. Calculate the value of this temperature in Kelvin. Oh, okay, so that's actually just got to know the difference between Kelvin and Celsius. So Kelvin, all you have to do is add 273. Okay, because 0 Kelvin, okay, it's just a K, it's not got a degree on it. It looks weird, it's like okay, doesn't it? 0 K. Is minus 273 degrees Celsius. Okay, it was made so that there would be a 0 for calculations, because in lots of calculations you can't have a minus. So we get to, even got some in this paper. Okay, we can't use a minus. Right, so 0 K. So what we've got to do is add on. So 23 plus 273. So 293 Kelvin. Yeah, it's not a degree on it. A lot of people say degrees Kelvin, but it's not. A student changes the volume of gas in a container and notes the pressure for different values of the volume. The results are shown in figure 6 and plotted on the graph in figure 10. So volume milliliters and pressure in kilopascals. Okay, so they're changing the volume. This is what they're changing. And pressure. Okay. So it says pressure in kilopascals, volume in milliliters. Identify the anomalous result plotted on figure 7 by drawing a circle on figure 7 around the anomalous point. So it's probably easiest 1 mark I've got on this paper. That one. Okay, so I might not exactly, it's that one, sorry. Draw the curve of best fit on, yes, a curve, not a line. So let me just get some kind of pen. Can, yeah. Curve of best fit. So here we go. So I'm using a graphics tablet. Not to be exact. So we're going to go through. Oh, I've got a wiggliness. It's not a line, it's a curve. Okay. Describe how the graph of figure 7 would change if the student repeated the experiment with the same mass of gas at a higher constant temperature. Right. So the pressure would be generally high, wouldn't it? So the pressure would start higher, show the same type of curve, and end higher. So it would look like that. Sometimes they might want you to draw it on, okay? Figure 8 shows a small container of carbon dioxide at high pressure. The pressure P1 in the container is 8 megapascals. The volume V1 of the container is 14.5 centimeters cubed. The container is pierced and all of the carbon dioxide goes into a large balloon. The volume of gas V2 in the large balloon is 1,160 centimeters cubed. Calculate the pressure P2 in a large balloon. Use the equation P1V1 equals P2V2. So we're told what P1 is. We have to work that out ourselves, but we're told this time. So P1, let's substitute. So 8. Okay, times V1, 14.5 equals P2. Oh, we don't know that, leave that. Times 1160. Okay, so it's an equation. We can actually just work out what this number is on this side to make our lives a bit easier. So 8 times 14.5. So 116 equals P2 times 1160. Okay, so let me divide both sides by 1160. 116 divided by 1160 give us P2. Okay, and we get an answer there. So it's actually a lot easier than we probably thought it was. 1160, 0.1 megapascal. It seems low, but it's megapascal, it's like a million mega. Okay, so it's not actually that low. Here we go. Solid, liquid, and gas are states of matter. Which process describes the change from a solid to a liquid? Okay, so it's like ice going to water, and that will be melting. A student determines the density of the liquid. The student puts an empty measuring cylinder on the balance, figure 10A. The student then adds liquid to the measuring cylinder, figure 10B. Okay, calculate the mass of liquid added and the volume of liquid added. Use the information in figures 10A and 10B. Right, so mass, right, so look at the reading. So 230 minus 201, so 29 grams. There's one mark, remember, it's probably going to just be add or take away something. Okay, so I think I might cut off the, let's look at the volume. Okay, so volume, I think I might cut that question off, but we'll do it here. So we're just going to read off here. So between 20 and let's say 25 centimeters cubed. Oh yeah, it's centimeters cubed, just checking the unit there. Which equation should the student use to calculate the density of the liquid? Okay, so density is measured in kilograms per centimeters cubed. So its density is mass divided by volume. Okay, state 2 improvements a student could make this investigation. Okay, so look. The student tells the density of a liquid. Student puts an empty measuring cylinder on a balance and adds liquid. So you could repeat the experiment a number of times. And use a more accurate balance, because some balances go decimal points and things. Yeah, sometimes it's quite difficult to think of improvements to experiments, but sometimes you get marks of quite straightforward things. Figure 11 shows an electric kettle. Okay, like one you have in your kitchen. The kettle contains 1.5 kilograms of water. The kettle is switched on. Calculate the energy needed to raise the temperature of the water by 50 degrees. Specific heat capacity of water is 4,200 joules per kilogram Celsius. Use the equation, delta Q. Right, so calculate the energy. So Q is energy. Delta is a change in, so mass, 1.5 kilograms. C is the specific heat capacity, 4,200 joules per kilogram Celsius. And then change in temperature, need to raise it by 50. So all we're doing is multiplying numbers. Okay, so there's no rearranging going on here. 1.5 times 4,200 times by 50. So 315,000. So these sorts of questions, they're often going to be quite big numbers for energy, especially in boiling water. It actually takes quite a lot of energy. The amount of energy needed to bring the water to boiling point is 670,000 joules. The kettle has a power of 3,500 watts. Calculate the time T it takes to bring the water to boiling point. So you might have thought, well, didn't we just calculate that? No, we didn't calculate to boiling, it's 50 degrees. Boiling point is 100. That's why it's bigger. Calculate the time T it takes to bring the water to boiling point and use the equation. Right, then we're rearranging. It's 3 marks, so you're going to get some rearranging. Right, so power, 3,500 watts. Okay, so energy, 67000. Divided by the time. Okay, so what I'll do is times by T. $670,000. Then we divide by 3,500. Okay, so we've got T on its own. 670,000. 3,500. Can we just put in a calculator? Okay, 191 seconds. Okay, figure 16 shows a metal container with a movable piston. Right, so this can move. Might not have seen that. This can move up and down. So we've got point X is the inner surface of the container. The gas in the container is at a higher pressure than the air outside the container. So in there is higher in here, okay? So high. So we've got which of these shows the direction of the force due to the gas on the container at point X. So it's always at right angles to the surface. So it's C. So that's why they're tricking you with some of them, because it's not at right angle to the other ones. Okay. The pressure of the gas in figure 16, P1, is 120 kilopascals. The volume of the gas, it's similar to the other one, isn't it? The volume of the gas in figure 16, V1, is 2,500 centimeters cubed. The piston is pushed up slowly, so the temperature of the gas does not change, because we all know the temperature will affect it. The new volume of the gas is V2, 1,600 centimeters cubed. Calculate the new pressure of the gas, P2. So it's already been rearranged for us. So again, all we do, we put numbers in. So P1, 120. Right, we're going to put it as its whole number, 1,000. So it's kilos, 1,000, times V1. So V1 is 2,500. Divided by V2, 1,600. So these numbers look quite big, but yeah, that's you can't do that with a calculator. Right, so do 120,000 to 0,000 times by 2,500. Okay, and then we divide that by 1,600. So we get an answer 187500. Right, that's pascals. So we need to put that into kilopascals like the answer. So what we need to do is divide it by 1,000 to put it into kilopascals. So equals 187.5 kilopascals. So thank you for listening today. Good luck on your exams and hope to see you in a future video. Thank you. Goodbye.